Right. Hi, everyone. Welcome to our uh, kind of the end of Unit 1 and the beginning of Unit 2. We are now going to be looking more specifically at the astronomical concepts that are necessary to analyze our data. And so we're going to finish up with just a quick look at how telescopes work, and then some specifics of binary star systems in general. And then toward the end of our meeting today, we're going to go into the Unit 2 block, and if I could get you at some point to turn on your computers and go to Unit 2, then we won't have a big time delay in people booting up their computers. And then we can open up Stelladopy, and I can show you some of the parameters that we will enter in order to start searching for our binary star system and get our research projects rolling. You'll also probably notice that if you haven't seen it yet, I have put out a Get Acquainted um, little, I guess it's technically a quiz because it's worth 5 points, but what it is really is just an opportunity for me to get to know you better so that I can properly assign you a lab group that will be most suitable to your uh, um, interests. And so as soon as I can get that information from you, I'll try to find the best matches for our different groups. And then we can, next week, what I'm thinking that we could do is I'll give you some of the basics for how to start looking for a binary star system. And so if you are so inclined, you could use some of those ideas and start looking this week. And then I can set up some kind of a Google Sheet thing so that you can put your name on it and show you how to do a link to the binary star system that you are interested in. And you can pull up a couple of them. And then when you start getting into your groups, you can share what each of you has found, and you can decide on which binary star system you think would be the best one for you to do your research on. And so that's kind of the plan for today, and that'll continue on through next week. As soon as we get the star selected, the star system selected, then we can talk about the getting the photograph of the star system and make sure that that photograph is going to show up so that we can clearly see both stars, so that we have something that's good to analyze. And so that is the plan for today, and that'll carry us into next week. Are there any questions? Okay, well, let me then share my screen with you. And a couple of last topics. Now, what I've done is I've moved these topics over to Unit 2. So I'll be giving you a one or two more quizzes on the subjects that I am covering in the first part of the lecture today. And so then those will be due before next week. And then if you have any extra time left over, you can start looking for a really good binary star system. Now, when I say binary, I don't necessarily mean that you have to limit yourself to a binary system. There are triple star systems, there are quadruple star systems. Oftentimes, only two of the stars would be visible in a more extended system like that. But if you wanted to try to find something that was a little bit exotic, and it looked like you could get good pictures for it, that is certainly something that you could consider. Okay, so let me just talk a little bit about telescopes. You're probably familiar with the normal refracting telescope. A refracting telescope has two lenses. And so typically then you have an eyepiece lens and an objective lens. The objective lens is where the light comes in. Light comes in this way, and then it is magnified and brought to a clear focus in the eyepiece lens. Now, refracting means that there are lenses all the way through. So there's two lenses, the primary and objective lens here, and the eyepiece lens. Typically, the objective lens is fixed, and the eyepiece lens in a normal observing telescope can be adjusted. You can put in a different eyepiece lens, and so it's in the eyepiece lens that you can control the magnification. By putting in a more curved lens, you can get a greater magnification. But these are limited because of the size. It's hard to make a large, accurate refracting telescope, and so they tend to be small. And they don't have great light gathering ability. The telescope is basically a big light funnel. It brings in light and it allows you then to magnify, but it doesn't do any good to magnify if you don't have enough light to work with. And so the larger telescopes, the kind that we're going to be sending out our orders to, are the reflectors. So they actually use a curved mirror. And in a reflecting telescope, what you have is a curved mirror, a long tube like this. And so this is where the light comes in. And then this is your mirror. And it's curved. The perfect kind of a mirror is a parabolic mirror. But sometimes for smaller telescopes, spherical mirrors are used because they're a little easier to machine. So the light comes in like this, and normally that light in a parabolic mirror would be brought to a point of focus. But before it gets to a point of focus, you have a second lens, or a second, in this case, it's a mirror, here, a curved mirror that can bring the light out to a point that's outside of the telescope. There's a little hole here that so that the light can go through, and then here you still have a lens. So this is your eyepiece lens. Now the advantage of this is that you can make this kind of a telescope much larger. And with a refracting telescope, if you tried to make a refracting telescope big, like these reflectors, you have the problem of the lens actually bending because of the influence of gravity. And so that would make it inaccurate. The Hubble Space Telescope, so reflecting telescope, and it had a slight variation in the curvature that was only about 1/10 the diameter of a human hair. That's how far off the curvature was, 1/10 the diameter of a human hair. And it needed a pair of eyeglasses because of that. It didn't work properly, and it cost us $1.5 billion to send up a mission to the orbiting Hubble to give it a pair of eyeglasses. So normally this is where you'd be viewing. There are other kinds of focuses too, where instead of having a curved mirror here, you have a mirror that bounces the light to the side of the telescope like this. And so that can be done. So sometimes you'll see a telescope and people will be looking through from the side. But the bigger telescopes tend to have the observer at the backside. Now, the kind of telescopes that we're going to be using are robotic telescopes. And so instead of having an observing position, what you have here is a camera. And then the telescope is very much like a clock in that there is a mechanism that can rotate the telescope to keep pace with the motion in the sky. And so the robotic telescope then is able to, it's aligned properly, it gets the coordinates, and the computer then rotates it into the right position. It takes its picture, and then that picture is sent off to us. Now I'll be showing you next week, but we have these robotic telescopes stationed all over the world in the northern and southern hemisphere. So here in this is like Europe here, this is Africa, then Asia, and so there are telescopes in the northern and southern hemisphere. And they tend to be pretty big. Some of them have aperture diameters that are 1 meter wide. That's like more than 3 feet wide, which means they have tremendous amounts of light gathering power. And so when we make our order for a particular coordinate to take a picture at that point, then from that array, a decision is made based on the availability of that telescope and also which one could give the best picture as to which one will take the picture. And then that's turned into a computer file that will be sent to you in a zip file, and then that zip file can be analyzed. And so that, just kind of in a nutshell, is what we have going in terms of the telescopic viewing. And so we won't be doing any viewing ourselves, but we will have the ability through this array to have these pictures taken. And so once we see that we have a good picture, then we'll take 10 pictures. And then you'll basically take those 10 pictures and you'll do 10 separate analyses, basically finding the R and the theta, the rho, which is the distance between the stars, and the angle with respect to the primary stars. And then that's the way that we'll analyze our data. Okay, so that is the telescope overview. Are there any questions about that? Okay, now the other thing I wanted to talk about in a little more detail is the actual details of some binary star systems and how they relate to what we're going to be studying. Okay, so there are different types of binary stars. So ones we will study will be regular hydrogen-burning stars that are in a pair. Now, when I say hydrogen burning, I don't really mean burning like burning coal, but rather this is a very loose and sometimes misunderstood term meaning hydrogen fusion. So stars spend most of their life in the hydrogen fusion stage. And in hydrogen fusion, we have 4 hydrogen atoms, which are basically 4 protons. And if we have very high temperatures, they can be converted into helium. But it takes tremendously high amounts of heat to drive the hydrogen atoms close enough together so that they can then, and then there's another force that's even stronger because you have the repulsive effects of protons that would tend to make them fly apart. But if you can get them close enough to each other, it's like there's these little hooks that can engage, but they're very short range. And those hooks, not really hooks, but that represents what's called the strong nuclear force. And so the four hydrogens then turn into helium plus energy. And the energy comes from a little bit of the hydrogen being turned into helium. This energy is basically about 0.7% of the mass of the hydrogens is turned into energy. And that's what causes a star to shine. And so inside of the core of a star, this is where it's hot enough, maybe in the case of our own sun, 27 million degrees Fahrenheit. And so that releases energy. And it doesn't seem like very much, only 0.7% of the mass. So the helium atom is 0.7% less heavy than the hydrogen. So if you put the hydrogen on one side, the helium on the other side, the hydrogen side would go down, and the helium side would pop up because it's just slightly lighter. But because of Einstein's equation, E equals mc squared, even a small amount of mass, when multiplied by a huge number, the speed of light, gives rise to a huge amount of energy. And so the star then shines steadily, and there's a balance between the gravity forces that pull inward and the fusion forces that push outward. So this is like a hydrogen bomb that's constantly exploding, but the gravity keeps the nuclear monster in check so that the gravity forces pull in just as hard as the hydrogen fusion forces push out. And so these are the kinds of stars we'll be studying. They'll be what we call main sequence stars or hydrogen burning stars. And so they will have a certain brightness, and so they'll come in pairs. And they'll be orbiting around each other. Is this the only kind of binary star? No, there are much more exotic kinds of binary stars that we won't be able to take pictures of, so we won't be able to study them, but there are other types. Briefly mention them. You could have what's called a white dwarf, which is a star that at the end of its life has shrunk down to about the size of the Earth. And then surrounding that, you could have a normal star. And that normal star could dump matter down the white dwarf star and cause the white dwarf, cause little explosions to happen on the surface of the white dwarf. And so that's what's called a nova. And so you can get in a binary star system in which one of the stars has lived out its life, it's run out of hydrogen and is crushed down to a small size. You can get material from the other star landing on the surface and exploding and producing explosions. And so that's what a nova is. You could also get a black hole and a neutron star orbiting around each other. Or a black hole is essentially a star at the end of its life that's been smashed to zero size. And a neutron star is a little bit lighter star than a black hole, but still very dense. 1 tablespoon of neutron star material might weigh 1,000,000 tons. And so these are all examples then of more exotic binary star systems. But again, we won't be able to take pictures of these because they're not putting out the kind of light that our telescope is able to pick up. And so there is some more information about binary stars and about the evolution of stars that you can look through, but I would, on the quiz, I would only ask very basic questions regarding that. Are there any questions about that very brief overview of binary stars? Okay, now for to get more specific into the kind of binary stars that we're going to be studying, we're looking for binary stars that are similar in magnitude, okay? Because if we have stars that are too different in magnitude, then a telescope that is trying to take a picture of both of them at the same time probably won't be able to see the dimmer one. And so the dimmer star should be uh, probably within a factor of 100 as bright as the main star. So this is our main star. This is our primary star. And this is our secondary star. This is the dimmer one. And so typically then we want a difference in magnitude around maybe 4. Okay, and so in other words, we could have a magnitude 9 and a magnitude 13. And the magnitude 13, although it's a bigger number, a, a, a difference in 5 in the magnitude is associated with about 100 times less bright. Okay, and so we don't want to go quite that far, but we can go a difference of 4 in magnitude. It'd be maybe 40 or 50 times less bright. And we should still be able to pick up both stars, as long as their difference in magnitude isn't too large. The primary star, we're essentially looking for magnitudes that are reasonably bright, because if the primary star isn't bright enough and the secondary star is too dim, then we won't be able to pick up one of the stars. But typically we're looking for something like magnitude 9 or below. Now remember, below here means brighter. As you get to lower numbers, the magnitude goes up, not down. And so every change in magnitude, we talked about this in an earlier lecture, we change by 1 in magnitude. That's a difference of about 2.5 in brightness. And then if you go down 2 in magnitude, it's 2.5 times 2.5 times brighter. So it goes logarithmically, so that each change of 1 in magnitude is an extra factor of 2.5. And so that's when you start doing that, say 2.5 times 2.5 times 2.5 times 2.5 times 2.5, you do that 5 times, you get about 100. And so that's why a difference of a magnitude of 5 would be 100, and that's a little too much, so that one of the stars then is going to be so much brighter than the other that you may not be able to see the secondary star. Okay, so that's those are the parameters that are involved with brightness. We also are interested in a certain separation distance. And so the separation distance should be somewhere between 5 and 10 arc seconds. Okay, and so this is an angle then between them as measured from our point of view. Remember that an arc second is equal to 1/60th of an arc minute, and it's equal to 160 times 60, or 1/3600th of a degree. Okay, so an arc second is just one, because there's 60 minutes in a degree and 60 seconds in a minute. There's 3,600 arc seconds in a degree. And so we're looking then at somewhere between 5 and 10 arc seconds from our point of view. Now, if these stars are orbiting around each other and they have that kind of a distance, typically they're going to have very long periods. This is from Kepler's third law. T squared equals K A cubed, where A is your typical distance and T is your period. And so what this means then is that we'll be, for the most part, looking at star systems that have a period of hundreds of years. Just because of the separation being this big, that is kind of like what our A is here. So when you work this out, it means that the periods could be hundreds of years. Since we're plotting out the orbits of these things, we are only going to be looking at a fairly small segment of the total orbit. And so let me just clear this out a little bit here. Usually we like, even though they're orbiting around each other, we like to start with the primary star and then look with respect to the primary star what the secondary star is doing. Okay, and so if the secondary star, let's say, is here and it's moving around like this might be its position, say, in 1925 when it was first measured. And this might be its position in the year 2015. And so you see that there's a relatively small part of the orbit that we're plotting here. And so then we'll put our data point in along with the other ones. And our data point then will help us to constrain the orbit and to try to predict what the overall orbit will be. And so we'll be measuring the distance between them, rho, and with respect to some position coordinate, which is usually north, we can measure theta. Okay, so from the north, we measure theta around this way, where this is kind of a funny way to measure it, but from the north around like that. And so those will be the two pieces of information we'll get, but we'll expect that we're usually only going to be seeing a little piece of the orbit. When we look at the other data points that have been gathered, it won't be a huge portion of the orbit, simply because if they were closer, let's say we started going with 2 arc seconds, then we might be able to get much more of the orbit plotted in 100 years. But because the distances are smaller and t squared equals k a cubed. But our constraint is that we want the robotic telescope to be able to take pictures of it, which means it has to be separated by a larger amount. And so that automatically constrains us to star systems where all of the data will be collected within a fairly small part of the total orbit. And so we'll be looking for distances between the stars on the order of 5 to 10 arc seconds. And so this is just a little bit of preliminary stuff. But I think what we're ready to do now, this is about the right time to do that, is to go into Unit 2. So if you could all, if you have your computer on and you can go to Unit 2, maybe you could follow along with me. And if you're not able to do that, perhaps you're on a cell phone. It'd be very dicey to do that on a cell phone. But you could still just write down what I'm saying. I'm recording this too, and so you could go back over it later if you had missed anything, and so that you can still start to look at it and see if you can collect any data between now and next week. Okay, so that's where I'm going now, is to the computer. That isn't what I wanted. Let me just go back one. Try that again. That's not it either. Here. There we go. Okay, so now we're on Unit 2. I've clicked into Unit 2 here. You'll notice there's an overview. And there are a couple of things to read. Then here's some notes on double stars, a handout, a couple of video clips, and discussions of double stars and binaries. I'll be talking a little more about proper motion. Basically, with proper motion, what we're looking at is how fast are the stars moving and across the sky. They don't move very fast, but um, if they're both moving across the sky at a very slow rate, but it's the same slow rate, then that's a good indication that the stars are actually bound to each other. Because if their motion with respect to us is they're both the same, then it's not just a coincidental alignment of two stars that are actually taking off in different directions. And so we'll talk a little more about how we can check for proper motion, but basically what we're looking for is that the number of arc seconds per century that one of them is going to be similar to the number of arc seconds per century that the other one is moving. But it's not going to move much in a human lifespan, but it's enough to where we can get an idea as to whether or not they're real physical binary stars or whether they're just coincidental alignments of stars that would correspond to what we call an optical binary, or kind of a phony binary. It looks like a binary, but they're not really gravitationally bound. We're not as interested in those, but we are interested if we're not sure if they're physical or optical. Um, we want to make sure that we can eliminate the ones that aren't physical from consideration. And so that's why if you end up with one that is just an optical binary, but that you've helped to show that has contributed to our knowledge because it has eliminated it as an actual physical binary. Okay, but we'll try to find ones that are real physical binaries as we go. All right, so here's a little more stuff through here. And so you can look through this stuff this week, and then I'll add a couple of just kind of quick quizzes on these things. It's not going to be anything worse than what you've seen so far. And then down here near the bottom, here's Stelladopy. And so you should all have this link. And so if you can all click on this link right now, we'll bring this up. Now, normally Stelladopy, you would need to log in, but by using this link, we don't have to log in. And so once you've gone to Stelladopy, basically what we have is a very large database of stars. And this is probably the biggest database of double stars that's available. And so what we're going to want to do first is go to advanced search. So once you've opened this up and you have a page that looks like what I have here, then you can click on the left here on that top one, and we're going to do an advanced search. And so this means that, and so you'll need to do this before you can start to, and we don't need to fill in everything here. There are just a few things that we need to fill in that will limit our search to the kinds of stars that we can get good pictures of. And so one thing here is the right ascension. Now this is important because
Excuse me.
certain-
I just want to let you know, I don't think you're sharing your screen. I'm following along and I'm on advanced search, but I can't really see exactly. It was like on a Google Docs page. Just want to let you know.
Okay, can you see that?
It's the same thing before. Am I the only one who's not seeing like?
Is
No, it's
everybody
on that. I was on the page, but it looks like a Google Docs thing or something over here.
Yeah, it doesn't look like the Canvas page, but I'm on the advanced search on the Stelladopy.
okay.
But yeah.
Okay,
I
so
can
but
follow
you're
along.
not okay, so you're not seeing this. That's
Yeah,
odd.
I'm hearing it. Yeah.
Okay. Okay, well, should be able to follow along if you can see what I'm seeing. I'm going to be doing this very slowly, and all I'm going to do is, well, what I can do is, after I've entered in a parameter, I'll go back to the whiteboard, and I'll just make sure that you're entering it in the same way that I am. That's what I can do. Okay, so with right ascension, are you seeing this? Are you seeing this now? Are you seeing my page right now? You're not seeing-
No, I can't see the page you're on. I
Okay.
don't think so.
So what I did is I just clicked, there's a link. Gosh, I
Oh,
don't
it's
remember.
the Doppy and advanced search, right? I could see the right ascension. I'm on that page on the database.
Right.
now.
So can you see this now? Are you
No,
seeing this?
your screen's the same still, but
What are you seeing?
it still looks just like a Google Docs page. Mm. But I liked your
Were you
idea.
able to see my unit 2 that I was showing you earlier?
No. Okay,
You weren't.
now I could
Can
see
you
it.
see it now?
Yes.
Okay. So here, we'll try this again. From here, there's a handout that says selection of double stars research. And I'm going to click on that. That's right above Stelladopy. Can you see this? What I just pulled up?
Yes, I can.
Okay. So what we have here, if I can just make this a little bigger, is a view of the sky. This tells us which right ascensions are visible at during which months. And so when you're looking away from the sun, there's a certain part of the nighttime sky that'll be visible, but the rest of the sky is not going to be visible because when the Earth is pointed in that direction, the sun is creating too much light pollution. And so because we're in February right now, we're going to want to go with a range of right ascensions from 5 hours to 15 hours. So that means that the other ones would the other stars would only be visible during the daytime. And so that's what I'm going to put in as my parameter for right ascension. So let me try to click on this again. And can you see this now? Okay, so it's working now. Good. And then I'm clicking on advanced search. Can you still see it? Okay, so now it's up. Good. I don't know what happened before. But okay, so what we want to do here with right ascension then is we want to make it between. Okay, so we're going to go between 5 and 15. So then click over here on the right, then you do a 5 and then a comma 15. Okay. And so that we're saying that we're only going to be interested in stars that are visible in February. And the stars that are visible in February, so that we're looking out in right ascension away from, there's the sun. We're looking away from the sun on the nighttime side of the Earth. But by the time the Earth rotates around to this side, the sun is there. And so you can't see the other right ascensions. And so that means the telescope couldn't take a picture of it because it wouldn't be visible. Now with declination, we don't need to worry about that. The declination is the angle toward the north and the south because we we would have a problem if we didn't have telescopes in the southern hemisphere. We can see the southern sky too, as well as the northern sky, because we have telescopes all over the Earth in the northern and southern hemisphere. So we can just leave declination alone. And we go down a little farther. Thank you for telling me that you couldn't see that. I hope that always let me know if something isn't working on your end. Okay, so we're going to be looking for here now. The next one I would go for is the magnitude of the primary star. And so we're going to want it to be less than or equal to, let's make that, for the moment at least, let's make that a 9. Okay, so anything less than 9 then is actually brighter than that. So we're interested then in a primary star that has a magnitude of 9 or below, but below, remember, if you have a magnitude of 0, that's actually really super bright. And so it's the magnitude 10, 11, 12 that we'll be looking at then as being the magnitude of our secondary star, because it'll be less bright than the primary. So you'd want to put in a 9 there, less than or equal to, as the magnitude of the primary. Now, we don't need to put in the magnitude of the secondary, but we can do a delta magnitude here. So let's do a delta magnitude here that is equal to delta magnitude. Let's make it less than or equal to, between, no, let's do, let's see, for this one, delta less than or equal to 4. Okay, so in other words, the magnitude could be, the difference in magnitude could be 3, it could be 2, it could be 1, or it could be 4. Less than or equal to. So that's what we want for that one. And then the separation, we're going to want this in arc seconds. And so you're going to want this to be between 5 and 10. So what we can do here is do a 5, comma, 10. So you want that comma anytime that you're entering in 2 numbers. Like for a between here for right ascension, we did 5, comma, 15. And so that means 5, 6, 7, 8, 9, 10, anything between 5 and 15. And here this is 5, 6, 7, 8, 9, 10, anything between 5 and 10. We don't need to worry about spectral class, all of that. As long as we get something that has the right magnitude and the right difference in the magnitude, we should be fine. So we're not putting any more specifications on this. And then a couple other things. We don't want visual binaries, but we do want visual double and uncertain double, because it's either been proven to be a double, physical double, or we're not sure. And so that's uncertain double. And so either way, we want those, but we don't want to be looking for example, a physical double. And so we'll just click on those two. Okay, so is everybody with me so far with this? Everybody able to do what I did? Separation between 5 and 10. Delta magnitude less than or equal to 4. We could go a little farther with this, but if we go to 5, then one of them is going to be 1/100th as bright as the other. So it's possible that the second one won't. If the second one doesn't come out, then we're out of business, because you have to have 2 stars to compare them to each other. With the magnitude, it's okay for it to be brighter, but brighter means less here. And so brighter is less than or equal to 9. And then here, we want it to be visible in February. And so our right ascension is between 5 and 15. And so once you've got all of those filled in, then you can search. So you can just click on search the database. And so now a whole slew of stars are going to come up. And so up here, there's a few things that we're going to be looking for. One is, I'm sorry. There's one other thing we needed to do. Let me just go back. We want the last observed. Let's see, where is that? Date last. Okay, now the reason why we want we want to put a specification on the last observed is that if somebody just did a report on this in 2022, then we're not going to really add anything because it's going to have hardly moved at all since 2022. And also there could be duplications because if we have other classes around the country that are analyzing this stuff, this kind of a class really kicked in around 2016. And so if we want our work published, then we don't want to just duplicate something that some other student did in another class. And also, it would be nice if we could have just a little bit of movement of the star since the last data point was taken. And if the last data point, say, was taken in 2015, this would give us an opportunity for us to get something that's a little more unique in terms of its position that would give us unique information about it. And so date first, we have no limitations on date first, but for date last, let's say, oops. What we want here is less than 2015. Okay, so we want it to be earlier than 2015. And so there are other possibilities. Well, we can make it less than or equal to. Let's do that. Because 2015 would be fine, but then anything earlier than that. Okay, and so that way we're not going to be duplicating somebody else's work and then having it rejected for a publication. Okay, so now we'll go, and so let's see how many stars we have. We started out with a few 100,000 stars in our database, and now we're down to 273. Okay, so our specifications have narrowed down our search from hundreds of thousands to a couple of hundred. And so what is it that we're going to be looking for here? Well, and I can kind of summarize some of these things for you. Less than, it's funny.
Dr. Reckmeyer.
Yeah. Did it go out again?
No, it's fine. Just mine says it has like 260 something instead of the number that you got.
Yeah, I don't know. I don't know.
I'm pretty sure I put in everything that you said.
Yeah, it could be just slight differences. I put in very similar parameters this morning, and I got a different number than I just got now. So, but I don't think that that's anything that you did wrong.
Okay. Just in case, can you like not right now, but maybe like later, write down all the criteria that we should search for and then put it on the Canvas page?
Yes, yeah, I'll do that. I'll make sure that you've got that. And so These are our
Okay.
pages. So this is page 1. So we've got different pages here. Now let's just go back. That last thing. So let's just take a look. Here we've got the last observation. And this is the next one over is the number of observations. Okay, so I'd be concerned about just one because that was in 1895 and it hasn't been looked at since. And so maybe there's something wrong with it. Because it seems like that would have been looked at more often than just once since 1895. But I'm not necessarily looking for something that has 20 or 30 either, because that seems like it's kind of been overstudied a little bit. So I might go for something that's somewhat in between. Okay, and we could, for example, have 7 observations. That sounds kind of interesting. You have a separation of 8.8, a magnitude of the primary 8.84, magnitude of the secondary 12.3. So this one is quite a bit dimmer than that one, but the difference in magnitude is 3.46. So it's below our criteria of 4. And so what we could do then is we could, let's see here. For some reason, I don't have the whole page on here. Can't click all the way to the left here. Try to move this a little bit to the side. Something's happened. Oh, there we go. Okay, finally. All right. So then what you could do then is click on this left-hand thing if you wanted to check one out. So let's check that one out. And so this is what's going to pop up. This is going to be a more detailed look at each individual binary star system. And so this will show us some important information. What we're looking for here, this is our angle. Okay, so this is the angle, and we want to see that it's changed somewhat since the last observation. The last observation was in 2015. The first one was in 1928. And here's the separation. For the first observation is 10.5 arc seconds, and the separation for the last one is 8.7. So there's a fair amount of change there. So that this looks like, now if this said 10.5 and then that said 10.49, then I would say, well, then all the points are kind of on top of each other, and you're not going to really add much to it. But if you can see that there's a little bit of separation here, 10 to 8.7, then that means that we'll probably be able to add a data point, and there'll be some kind of a continuity with it, but it won't just be exactly right on top of the last data point. And the fact that the separation distance has changed is good. But there's one thing that I just noticed here. Everything was looking great, but I probably should have looked at this first. So this double is not physical. Okay, so forget that one. But let's say that this had been a good one. You could then, up here on your link, you could copy that link and then paste it. And then that'll bring you back to Stelladopy and will bring you right back to what you have right here. So I'm going to go back because this said the double is not physical. It's probably the first thing I should have looked at. Because if it's not physical, and they're sure it's not physical, then it's not something that we're interested in. So let's look at another one. This one has 9 observations, separation 5.8. So they're a little closer to each other. Now, that's within the parameters that we're looking for, but it means that the period is going to be a little faster. If the period is a little shorter and it's moving faster, then that means that we may get a little better look at what at a new point on the orbit. That isn't just right next to a previous point. We might get a little bit of scatter there. This last was done in 2015. And the difference in magnitude, 3.09. So these are a little more similar in magnitude. So let's click on that second one. Okay, and so this says, notice down here, this is probably what you should look at first. The nature of this double is uncertain. Okay, so that means they don't know. So that means we could really contribute something here, because we could either find out that it's an optical double, or we could find out it's a physical double. How would we do that? Well, if we plot our data point and all of the data points are along a straight line, then and it's not curved at all, then it looks like they're just drifting farther apart. It's just a coincidental alignment. But if they're in orbit around each other, then you'd expect a little bit of a curve with all of the data. And so we could look here and we could see, well, when was this first studied? It was first studied in 1925. Okay, and the last date of observation was 2015. There were 9 observations. Now let's look here. We want to see if this has moved at all. So, well, okay, that's going from 234 to 233, so it hasn't moved much. And here, 5.6 to 5.8, the separation. So that's not ideal, because we're not getting a lot of movement in this case, that would be in about 100 years. It hasn't moved that much. So if it hasn't moved that much, then we're not necessarily going to have great data. Our data is just going to kind of be a bunch of points that are right next to each other that have hardly moved. And so we want to have some kind of movement. So go back and look at another one here. Okay, so okay, well, let's just try this one, the one that says 16 on it. This one. Okay, that has a separation of 6 arc seconds. So that's kind of within the smaller range, which means there could have been a fair amount of movement. I got a magnitude of 8.37 and 10, so not a huge difference in the magnitude. That one's looking somewhat promising. Uh-oh, said the double's not physical. So back to the drawing board. And so this would be the kind of process that you go through. Let's see here, this one with 11, 6.7 separation. Let's try that one. Okay, this one is uncertain. Okay, so that's a possibility. And we look over here, the first angle, 129. And, oh, look at that. It's gone from, oh, no, that's also 129. So it hasn't moved at all. So there's a little bit of change in the separation, but the angle has only changed since 1832. There's been very little change in the angle. So, it's a process of going through and seeing what you can find. And so you go through, you could go with one that's been studied a little more, but then there may not be quite such a unique contribution. And so I would be more interested in ones that were, this one only had 2 observations in 1991. So you'd wonder why there were only 2, if there's something wrong with it or not. But we've got a big difference in the magnitudes here, 8 to 12. So let's just try this next one down here. Oh, there we go. Okay, so for this one, we're going from 3 to 3.4, 7.4 to 7.8. First observed in 1893, and last one in 2015. So that's a possibility. So that one, I think, it shows some change in the angle, showing some change in the distance. Ideally, we might want a little more of a change, but that's the kind of process that we go through. Now, if it turns out that um, wait, this says it's not physical. Whoops. So we should have looked at that first. Okay. So that one's not physical. So anyway, that's the process that we go through. And so what I'm recommending then that you could do is see if you could find a few stars that look like they might be reasonable. And let me just kind of summarize some of the things that we would want to, for the qualities of the star that we'd be looking for. So it's kind of a delicate balance, but we'd be looking for something that's been studied but not too much. So I would say that anything less than like 2 observations would be too few. But if you had like 50, for sure that'd be too many. So we'd be looking for maybe 7, 9, 16 might be okay. Those kinds of numbers would allow us to make a unique contribution. We're looking for something where it's, if it says not physical, omit it. But if it says uncertain, that's okay. Or if it says it's a physical binary, that's also okay, because we can get more information about it, even if it's known to be a physical binary. Okay, and so these would be positives. We're also looking for a little bit, at least some change in the angle. It'd be nice if it were a few degrees. And a little bit of a change in rho, the distance. Over a fair amount of time. And so we might say over, say, 100 years. Because typically that's what we're looking at is data that might have first been gathered, say, in the late 1800s, early 1900s type of thing. So we're looking for something that's been studied not that many times, but over a fairly long range of times. So I'd say at least here 100 years from the earliest to the last observation, but not that many observations in that amount of time. And so it's a little bit of an art to try to pick those things out. But if you want to give that a shot this next week, and then you can take those results and you can combine them together with your teammates. You'll know who those are next week. then you can decide from between the things that you found which one might be the best candidate. You might want to save one or two of those and then run them by me. And then I could look at them with you and see whether there's anything that there might be a problem with them. But once we get the teams, combine your result, combine. There'll be a place where you can post your links. Then I can look at them. And I can get the opinion of Rachel too, who has been doing this for many, many years. And then we can decide on it. And then once we've decided, then we take the picture. So we may get to the point where we're ready to, at least some of you may be ready to try to get your first snapshot of it next week, but definitely 2 weeks from now, I'll be taking pictures of your binary systems. And if it turns out that we can't get a good picture, then that's why it's good to have a backup. So if you have one or two others where you've got like 2 or 3 good candidates, then that's kind of where we're going with this right now. So are there any questions or comments? Okay, great. I'll be putting something up, some kind of a Google Doc thing that within the next week that you'll be able to put your links onto so that you can all look at them together within your teams. And then next week, once we've got the teams going, we'll break up into breakout rooms, which we can do here on Zoom. So each team can be in their own breakout room. You can kind of talk amongst each other, get to know each other a little bit online, and then I'll be able to jump in and out of each of the rooms and see how you're doing. Does that sound good for everybody? Okay, well, let me know if you have any questions or problems, and if I don't hear from you, I'll see you next Thursday.
Hey, so unrelated to the astronomy stuff, Mark suggested I ask in physics class, but I forgot. What lab manual should I search up for the Millikan oil drop experiment?
I'll put something up for Millikan
Okay.
over the weekend.
Cool. Then I won't worry about it.
Okay, good.
All right. Thank you.
Sure.
Hey, I just wanted to say I was looking through there and I found a pretty cool one.
Did you?
And I think it's got like it was first observed 1894, last 2015. Its first wait, what does SEP stand for?
Separation?
Separation. Yeah. First separation 6.4 and last 7.928.
Oh, that's sounding good. And what did it say for the description? Uncertain?
Yes, uncertain.
Oh, good. And what about the angle?
172 and 174.
Okay, that sounds reasonable.
Yeah, it sounds
I think you might have already found one. Good job.
cool. I have
right.
that written down. That was the best one I found while we were doing the class.
Yeah. Yeah. Well, I would want you on my team, that's for sure.
Well, that's an honor.
All
Okay.
right.
Yeah, cool.
Well,
I'm excited to get a picture.
Pardon?
Oh, I'm excited
Oh, yeah.
to get pictures
Yeah.
of these.
We'll check that out and we'll go through the procedure for getting the picture next week.
Cool. Also, like, how do more observations get added? Because like obviously like we're gonna add observations through this course,
Mhm.
but like could just any amateur astronomer like be able to add observations?
They can add them, but it has to be something that's been published to be added. And so it'd have to be written up as a publication to be an official ad.
Hmm.
So once you've written up your publication, then that'll put another tick on the observations.
Cool. Because it seems pretty cool to just uh if I were to have that time like over the summer or something to like add some to some of those, because I really love doing that.
Yeah, that'd be really cool. Yeah, there's a thing with telescope time, but if you're not using up too much telescope time, you could you, you could use the time that I have available for that. So that would work.
Cool. Okay.
All right,
Yeah.
good.
Thank you.
Nice talking to you. See you next week.
You too.
Bye.